In this lecture, now that we've introduced the use of matrices to transform a vector, which typically we're thinking of as a force or displacement vector, um, uh, now we're going to look at those transformation matrices and just talk a little bit more about some of their properties. The first property that I want to talk about is the ability to reverse the transformations that we had talked about. So again, this time, we've been using P before, but this time we can talk about axes if we want. We don't have to list this. Once we have the Cij, we can use them to relate not only a force or displacement vector, but think about it. By definition, the axes themselves are related. You know, the new axes and the old axes are related by that transformation matrix as well. That's how we got it, right? So you can use it to transform any vector, including the axes themselves, right? And so we're going to show that here, where x1, x2 were the original axes, and we formed our Cij, you know, from this to the new coordinate system. And of course, then you can, look at, I'm just like messing up on my notation. You can, of course, use, therefore, I mean, since it came from it, you can certainly use the matrices to transform the coordinate system itself. No surprise there. So this is what I'm doing now is relatively trivial. We did the more general case, which is that there's a force or displacement vector, you know, sitting out there, and we transform it directly. That's really the more powerful case, right? Because the Cij allow you to transform it without having to even think about the second coordinate system. It just automatically puts it there. Here, we're kind of going back, and since we have the Cij, we're like saying, well, of course I can use that to transform my axes back and forth anytime I want as well. And you would be saying, well, okay, if you understand what I'm saying, you'd say, Professor Fitzgerald, that is true, so why are we doing this? And the answer is actually only to do the reverse transformation, right? Which is to say, you know, what happens if we want to then go back? So if the x1 and the x2 and the x3, these are all the old coordinate system, and this is the new, then, you know, we write like that, right? And that's actually how we got the Cij. And the only reason we're writing this now is to say, well, what happens if I want to do the opposite? Well, you notice I put a little wiggle there, and you could also have written this, the same notation. It's the same thing as, and then sometimes you'll also see these with brackets around them because they're matrices. Okay, so they're all this notation is the same thing. Oh, and there's one more. How can I forget that one? Which is the inverse of that. And that's because it turns out, and we're not going to prove it here, but if I have Cij, which goes from the old to the new, then Cji goes from the new to the old. So literally you just switch the subscripts, right? And so that's a very convenient thing. It's a little bit dangerous because now the notation really means something. We're going to talk about transforming tensors. And if you just arbitrarily start flipping these around, you're actually, changing the wrong coordinate system. So as powerful as it is to say, I've got my Cij, now I have something in the new coordinate system, and I want to transform that vector into the old one, right? You just literally change these guys around, and you can do it. Of course, the danger is that if you start flipping these guys around in all these formulas, and admittedly, as powerful as it gets confusing, right? Then it's very dangerous. So, this is essentially the inverse, then, right? Of that. So we're going to use this later. So it's important I like this language of old to new and new to old, which if you ever want to get a book that kind of goes over a lot of the stuff in greater detail, Nye, N-Y-E is the book, and it's a great book. Kind of goes a little too much into properties of materials that are best done in other books instead of just thinking about tensor notation, but it does mostly tensor notation and leaves a lot of the details but still it goes into a lot of detail. It doesn't have to, but the they use old and new and old, and I like that language a lot because it really clarifies why in some cases you're flipping these when you look at these longer derivations. Okay, so that's probably one of the most important one of the important properties of Cij is that to transform back, you just flip the indices, and that's the transformation matrix that sends you back. But let's talk about other properties. So another property of Cij is that if I calculate the determinant of Cij, it's 1. So that's called a unitary matrix. And it's really a function of the fact that, in our case, it's just composed of directional cosines. And so when you take the determinant of it, it will equal 1. Another property of this, because of all this, is that so another interesting property is that C11, C12, C13, for example, are components of a unit vector along x1 in this particular example. So if you think about the magnitude of x1 prime, then it's equal to 1. And of course, when you're doing the magnitude, it's C11 squared plus C12 squared plus C13 squared. So it's another property of this. And of course, that'll be true for any of the rows, right? I'm just using the x1 as an example. And the columns are also adding to become, the squares of the columns are the same, right? So if you go down C11, C21, C31, same thing, happens there. Another property is that we're looking at a Cartesian coordinate system here, then we know that x1 prime and x2 prime equals 0, dotted, right? So these are vectors, don't forget. And so therefore, C11 dot C21 plus C12 dot C22 plus C13 C. Right, so it's another thing, because if I dot the two, actually I might have messed up here. This is C23. Oh no, sorry, let's see. 1 1 1 1 2 1 1 2 2 2. So because x1 prime dot x2 prime in a Cartesian coordinate system, they're 90 degrees to each other. It's going to be 0. And C11, C12, C13 is from the x1, right? Remember, when you dot two vectors, you dot their components. x2 is C21, C22, and C23. And so the sum of those dots is going to equal to 0. And that's true again for any of the two axes. Finally, the last property that I want to emphasize about this is that Cij can actually equal a -1 if you move to a left-hand coordinate system from a right-hand. So let's say you go from a right-hand coordinate system to a left-hand coordinate system, you'll get a -1. Up here, this is for when I went from a right-hand coordinate system to a right-hand coordinate system. So a flip in the determinant value of Cij tells you that you've switched handedness in the coordinate systems. Okay, so these are all useful properties that we can use in the future, but in the next lecture I'd like to spend a little time going back and talking about why, a little bit more detail about why we need to use these transformative coordinates so often experimentally, and give you some examples.